Recording in progress.
We'll talk about DSP filtering and some of the other mathematical operations, kind of how a software-defined radio works, basic one, and how to do modulation and demodulation in digital signal processing. So some of the modern radios, I'd actually say almost all of the latest radios have at least some portion of a software-defined radio doing digital signal processing. They vary a little bit on the front end. There may be some analog circuitry there to change the frequency so they don't have to use as expensive analog to digital converters, because that's really the secret. You need a very high frequency A to D with a lot of bits, and those aren't cheap. One of the techniques is called direct digital conversion, where you take your RF signal, feed it directly into an analog to digital converter, and you get digital samples of that waveform. And then you process it in software or firmware, usually in a field programmable gate array or something like that. And that's called direct digital conversion, because you're going directly to the digital domain. There's no mixer circuit like we talked about, no variable frequency oscillator per se. This is an actual circuit of what the receiver in a ICOM 7300 is 2 chips. The RF signal goes straight into the A to D, and then it's processed digitally until you get to the audio output. This is kind of a block diagram. Typically, you'll have some kind of bandpass filter on the front end. You might have a low noise amplifier and or attenuator before the analog to digital converter. Once you get it into the A to D, let's see. David raised his hand. Hello, David.
Bob, can you hear me now?
Yeah, I can hear you now.
Okay, I'm sorry. I got a question. Okay, so this is how any kind of SDR works, I would imagine. But
Yeah.
in terms of frequency discrimination, how does that work? I mean, I know this is away from modulation, but in just quickly or in general, how does it, for instance, display or select a particular frequency?
It's all done digitally and mathematically. If you remember all those little equations I said that were there for the people that like math, you didn't have to remember them. Those are the equations that are actually being used in the digital signal processing to do this. So you're in the digital world, so you have samples, and you normally convert those digital samples, because they're time domain, into the frequency domain by doing Fourier analysis, and then you can do different things with them. It's a lot more involved than we need to go into for this exam. It's all done mathematically in the digital signal process. Typically, it's done because we generate I and Q signals, which we'll talk about in a little bit, which you're essentially converting things to a sine and cosine form, where the cosine is 90 degrees out of phase with the sine. So that's what I and Q actually stand for.
Okay, thank you.
Mix those together and do all kinds of wonderful things.
Thanks.
I think in this one, they're trying to show that you're sampling, which this F sub S is the sample frequency at 4 times the incoming frequency that you're looking for. Based on Nyquist sampling theory, you have to do it at a minimum of twice highest frequency that you're trying to reproduce. And then it shows that you go through the stages, what the waveform kind of looks like, where the original signal is and sort of the baseband. So what is meant by direct digital conversion as applied to software-defined radios? They made these very confusing. There's a lot of I and Q's in there. Okay. There's 2 basic things for an analog digital converter. One is the sample rate, which obviously determines the maximum bandwidth that you can operate on, because you have to have the sample rate needs to be at least twice whatever that frequency is. And otherwise, you get what's called aliasing. So it'll appear to be a lower frequency than it actually is. And I think this next one, if I can get there without double clicking, is showing we have a 1 hertz signal, and it shows what happens if you sample it at 0.3 hertz top. So you're only hitting every other one. So when you try to reproduce that, you're going to reproduce a much lower frequency signal than the actual. And so on at half a hertz, which is even worse because it's a multiple, and at 3/4 of a hertz. And then when you're sampling at 1 hertz at twice, you can actually reproduce the original signal. Normally, they'll try to do it more than twice, and 4 times is fairly typical, but it costs more to do that. What aspect of receiver analog to digital conversion determines the maximum received bandwidth of a direct digital conversion SDR? And the key there was the direct digital conversion, because some of the other forms of SDR, it's a little bit more complicated. And the sample rate on the A to D isn't the biggest factor as far as the maximum bandwidth. How frequently must an analog signal be sampled to be accurately reproduced? At least twice. Okay, the other aspect is voltage resolution. So we have to have a high enough sample rate to be able to operate on the frequency that we want to. we have to look at voltage resolution to see what's the minimum detectable signal that we can actually detect. And that's a function of the reference voltage for the analog to digital converter, because it compares everything to a reference voltage, where the reference voltage is the maximum output of A to D digitally. So depending on how many bits of resolution we have on the A to D determines what that lowest signal level is. So you divide the reference frequency by 2 to the n, which is the number of bits. So if it was a 10-bit A to D, then that would be the reference divided by 1024. Everybody knows there are 2 to the n's. So that's good. That's a good one to remember. 2 to the 10th is 1024.
No.
Huh?
No, we don't. Damn, dude.
Oh, yeah? How does that work?
F60 off thing that you have fun
Right.
and you 60 for 50 base. Here there's traffic in my
So you make a lot of money on that?
Say, yeah.
10 bits is 1024. That's a good one to remember. Okay.
We'll see you brother on the actual connection.
Yeah. So we'll do an example. If the reference voltage is 1 volt and we have a 10-bit A to D, okay, if we do the math, then each bit is approximately 1 millivolt. If you actually did the thing on a calculator, it's slightly less, but close enough to 1 millivolt. If we wanted that to be a microvolt, we'd have to go with 2 to the, geez, gosh, I'm rusty on that. 16, 14, somewhere around 14, 15, whatever. Where you get down, you can still have 1 volt reference. Depends on, you know, what your rest of your circuit needs. Because most of the receivers are going to be down in the microvolt range.
Yeah.
This is showing one type of analog to digital converter. It's called a successive approximation, where you start off and basically you feed it a 1 at the most significant position and compare that with your analog input signal. And if it's higher or lower, then the output is a 1 or a 0. So if it's lower than, let's say we have, well, it's got an 8-bit. So let's make it simple. Let's say it's a 4-bit. Okay. So if it was, and we're going to do 4 volts to make the math easy. If I had a 2-volt input signal, okay, and I send a 1, the most significant digit 1, compare it, I'm going to get a 0 because 2 is less than 4, right? I send the next most significant bit, which would represent a 4. and it's still higher, so I get a 0. I do the next one, which is representing a 2. It's going to be equal, so I get a 1. I do the next one, which would be equal to a 1, and it's going to be greater. So that's the out. So I keep doing that kind of process. Success. That's why they call it successive approximation. So you keep binary going through it. Trying to think, there's a name for that and some other processes, but essentially you're just trying every value to see whether it's greater or lower than, and come up with the actual digital representation of it. They work very well. They're very accurate. They're slow. You have to go through, depending on how many bits, you have to go through those steps for every sample. So what sets the minimum detectable signal level for a direct sampling SDR receiver in the absence of atmospheric or thermal noise? What's the minimum number of bits required for an analog to digital converter to sample a signal with a range of 1 volt at a resolution of 1 millivolt? In bits. Okay. A lot of the newer software-defined radios, I'd say most of them, basically split the signal into 2 data streams called I and Q. I stands for in phase, Q stands for quadrature phase, which means it's 90 degrees out of phase. So they're actually looking at the sine, which is the in phase portion of the wave, and the cosine, which is 90 degrees. And with those two, in DSP, you can effectively do the same thing that you do with mixer circuits to either generate or to modulate or demodulate. And this is kind of showing how you do it digitally, where you have sort of the equivalent of a mixer, which is really a product. So you're comparing the generated local oscillator signal, which is also done digitally. You're synthesizing the sine wave in the digital domain and comparing it with the I and T, which are shifted. So you're doing the I compared with the local oscillator that's in phase with it, and the Q with a 90-degree shifted local oscillator signal. And you sum those together and get a modulated signal out. You do the reverse for demodulation. And this is all done without diodes and resistors. It's all done with math in the digital world. So one of the things that's most often formed in digital signal processing is a fast Fourier transform, where you're going to convert a waveform that's been sampled in the time domain. So every sample is a period of time. It's an amplitude versus time. You're going to convert that to the frequency domain, where you're seeing amplitude versus frequencies. And you see this spectrum. That's how on the newer radios, if they have a waterfall, the waterfall is the result of an FFT on the signals, on the whole bandwidth that you're seeing. So every one of those little spikes that you see is the result of a fast Fourier transform. And then in time, you're just doing those samples and waterfall And normally, you get this discrete Fourier transform, which is slightly different variation of it to get the factors. Because when you're doing digital filtering, which we'll talk about in a little bit, you have to come up with the coefficients to multiply each sample by to implement the filter. And you do that by doing these discrete Fourier transforms on an impulse of whatever the waveform is you're trying to filter waveform you're trying to create. It gets kind of complicated, but this is why it's a little complicated. That's what's actually going on, where you've got 4 samples, okay, and they're in amplitude, both in phase and out of phase. So that's why you see the eyes in there. You do all this good stuff, and you come up with these coefficients, which is actually what you would use in the filter algorithm.
Jefferson Holder.
Yeah, I'm just thinking, who wants to date first?
Just so you know what's going on. A lot of stuff. Okay. Let me see. This one is showing, it's kind of weird, but up here we have this signal. The diameter of the circle, I think, is they're trying to represent the amplitude. And as we go through these, the amplitudes are going down. So these are like the coefficients of generating square wave. So you have each of these frequencies at different amplitudes. That's where the coefficients are coming in. And you sum them all together and you get this square wave. In the lower one, they're doing a similar thing. They're starting with the fundamental, which is a sine wave, and taking these multiples of it and coming up with this triangle wave. And this is just showing the time domain display of it versus the frequency domain. So you can see that the frequency spikes in the frequency domain that are represented by those. Don't worry, you don't have to reproduce that chart. It's there to confuse you. So what function is performed by a fast Fourier transform? Charlie? Yeah. You've probably seen fast Fourier transforms in real life. Or Fourier transforms, they should say. Have you ever seen a rainbow? That's Fourier transform. That's how it separates the white light into multiple frequencies. They actually use that optical technique. I went to a seminar 30 years ago, maybe more. The Army gave a presentation on some of their missiles, and they actually, and this was that long ago, they actually used prism in the front of the missile that did essentially it does in speed of light Fourier transform. And they compare the output of that with fixed images that were of tanks and all the various kind of targets we can recognize. It was really amazing. Not a lot of electronics, just a piece of glass. So we convert time domain to frequency domain. Okay, so we can filter a digital signal by using creating a digital filter. There's kind of 3 types. There's what's called adaptive, which is kind of a modified version of a finite impulse. There's finite impulse response and infinite impulse response. In the case of adaptive, they have a reference signal that they want the output to look like. So they compare the signal coming in to that reference signal and adjust the filter characteristics, the coefficients, in order to produce an output that is maybe an amplitude multiplied, but of that same waveform, follows the wave shape. I think that's what they're using on some of the newer power amplifiers that connect to certain receivers, and it's called DPD, where they do a similar thing and they can adjust and get rid of spurs on the output by doing this adaptive filtering loop. Then we have finite impulse response. It's called finite because the output of it will settle to its final value in a finite period of time. So you don't have infinite ringing type thing going on. An infinite impulse response is a recursive type filter, and it can actually never settle out depending on the filter and the input. So, and they're used for different purposes. The one advantage of the finite impulse is, and I'll show you a thing shortly, it's a fixed time delay, regardless of the frequency. It always takes the same amount of time for a signal to go through the filter. So there's no phase shift. Whereas in an analog filter, remember, you have a 90-degree phase shift that goes to 0, and then it goes to the negative phase shift, gets to the resonant point. That's not true with an infinite impulse. This is showing kind of the adaptive filter, where I'm still would like to see how these really work, because I don't know how you define the desired signal unless you kind of know some other things. You couldn't really do it at random. But one of the uses, and apparently a lot of receivers will have this type of filter as a noise filter for single sideband. Or so it says in the fine print. So a finite impulse response takes a number of samples, and they store them, basically shift them through, and multiply each sample by a set of coefficients, which are determined by, we talked about earlier, doing that DFT thing to get the coefficients, where you take, say you want a low-pass filter, and you would, at a certain frequency, you mathematically create an impulse form, which is just a pulse, and compute what the output of that would be, and that's how you generate the coefficients for that type of filter and what the cutoff would be. So every sample that comes in gets shifted down, and you're multiplying it by that set of coefficients. And each one of those stages is called a tap. Actually, I don't know why, but that's what they call them. And the more taps or stages you have, the better you can model the waveform. It's more accurate. Obviously, there's a longer time delay. So if you had 1,000 of them, in some cases they do, that's 1,000 samples delay before you're getting anything through there.
So you're basically taking, when it comes in there, you're taking the input, going into that Z minus.
XMN is your input.
Right, and then so it's taking the output of that square, then Z minus 1.
Right.
Comparing it in the signal down.
Well, yeah, those triangles are coefficients, and they're multiplied times the sample, and you sum them all together.
So that's not. To get more of those that you have.
Right. And actually, you can simulate one of these with a spreadsheet. And it's fairly easy. You got to do a lot of numbers, but because you can generate a sequence fairly easy, and you can easily do a low pass or high pass filter. And that's all they're doing, the same kind of thing. Now, like I said, one of the advantages is it's a constant delay, because doesn't matter what the frequency is, you're gonna shift X number of samples through that filter. If you've got an infinite impulse, and this is a very simple block diagram of one where it's a recursive filter. So you're taking the output and feeding it back in, multiple output samples. And in some cases, it's kind of a combination of recursive on the input and the output summed together, and really gets complicated. Obviously, they don't have a constant delay time through them, phase shift. Turns out they're more efficient to implement. You don't necessarily have to have as many taps for delay because of the recursion. So what kind of digital signal processing audio filter is used to remove unwanted noise from a received SSB signal? You have to guess?
Yes, like me,
Are you going to have a good guess?
yeah.
Well, I think A is a good guess. Okay. That's the only place I know where they're used. That's the only place I know where the adaptive filter is used, except maybe in the power amplifier DPD thing. Now, I'm not sure about that, but I think that's how they. Okay. Which of the following is generally true of finite impulse response filters, firmers? One thing that was different about finite versus infinite. Delay. Wow. Let's see, low battery. We talked about taps, okay, where each of those stages is called a tap. And obviously, the more taps, the more accuracy on the filter, and the sharper you can get the skirts, essentially. A digital filter can actually almost create a perfect square wave type of filter, where you can never get that close with an analog filter. Over here on the right is another infinite impulse response, more typical one, where you've got kind of two recursive loops. Where on the left, it's a standard impulse for finite impulse. What's the function of taps in a digital signal processing filter? Each one is a delay. Which of the following would allow a digital signal processing filter to create a sharper filter response? More of them. Okay, sometimes you'll see a thing called decimation, where your analog to digital converter is sampling at, maybe it's a gigahertz or something, and you're actually looking at a much, much lower frequency. So you have a lot more samples than you actually need, because as a minimum, you only need 2 per whatever the frequency is. And you might have, 1,000. Well, in order to help the processing, you try to get rid of some of those samples that you don't need, and the process is called decimation. And I think it actually came from you slice your enemy up into 10 pieces or something. But and it's not always divide by 10, but that's kind of a similar thing. You will eliminate a certain number of samples to get it down, so you have less samples to process. When you do that, okay, you have to worry about aliasing, because now you've got samples, at a much higher rate, even though you're throwing some of them away. Okay, they were actually sampled at a higher frequency, and you want to look at it at a much lower frequency, so you have to filter those higher frequencies out, so you don't effectively get aliasing again. And we call that an anti-aliasing filter. So it would really be a low-pass filter that's set slightly above the frequency that you're trying to process. And again, there's examples of aliasing where, because you've got to reduce sample rate because you threw a lot of samples away, you've also got to get rid of those higher frequencies. Otherwise, you're going to get an erroneous answer. So what's the function of decimation? That sounds good. Why is an anti-aliasing digital filter required in a digital decimator? Rid of the high frequencies. Okay. Back to I and Q. We can, in digital signal processing, we can use the I and Q data streams to both create a modulator and a demodulator by digitally mixing them together. It's really just a digital version of what you would do in the analog world in a regular receiver transmitter. One of the other techniques is what's called a Hilbert transform filter. And the reason it's used is because it's based on a finite impulse response filter. So you can generate a constant phase shift. So they can use a Hilbert transform to generate an I signal with a fixed delay, because it's finite impulse. And they can generate a Q signal with a 90-degree phase shift, but still a fixed delay. So the I and Q signals are still in sync, even though one's shifted by 90 degrees. And now that you've done that, okay, it makes it easy to get rid of one of the sidebands with the I and Q. Or so they tell me. I haven't tried to model that in a spreadsheet yet. What's the common method of generating a single sideband signal using digital signal processing? Yeah, don't let that big word scare you. It just means at right angles, 90-degree phase. What type of digital signal processing filter is used to generate an SSB signal? I particularly like that question.
It's sleep. It's yeah. Learning by interpretations. Gen. Yeah.
I think it would be better if they said that filter used in generating instead of two. Two implies that's the only way to do it. And that's all you have to do. It's a little more complicated.